Have you ever just stared at a big spreadsheet full of numbers and felt absolutely nothing? It's just a wall of data. But what if I told you there's a story hidden in there? A story full of patterns and secrets and insights? Well, today, we're going to find it. We're diving into how to organize quantitative data so it finally tells its story. I mean, think about any set of numbers. Test scores, housing prices, whatever. At first glance, it just looks like a jumble, like random noise. But I promise you, there are patterns and clusters and shapes just waiting to be discovered. The trick is knowing which tools to use to bring them to light. And that's exactly what we're about to do. So here's our game plan. First, we'll talk about why we even bother organizing data. Then, we'll look at tools for visualizing every single point. After that, we'll level up to histograms for those bigger data sets, learn to interpret the shapes we find, and then wrap it all up so you know exactly which tool to grab for which job. Sound good? Let's go. Okay, so this is that crucial first step. Before we can make any kind of analysis or draw any conclusions, we have to bring some order to the chaos. This is literally how we turn a boring old list of numbers into something we can actually interpret and learn from. So where do we start? Well, we're going to start with tools that are perfect for smaller data sets because they don't hide a thing. Both dot plots and stem and leaf plots let you see the overall shape of your data without losing a single original number. It's really the best of both worlds. You get the big picture and all the tiny details at the same time.
First up, the dot plot. And honestly, this thing is beautiful in its simplicity. It's literally just a number line. For every data point you have, you just pop a dot above its value. Instantly, you can see where the data is clumping together, where the gaps are, and what the overall spread looks like. It's a super powerful snapshot from a really simple process.
All right, next up, the stem and leaf plot. Now, this one might look a little strange at first glance, but trust me, it's incredibly clever. The idea is to split every number into two parts. You've got the stem, which is all the digits except the last one, and the leaf, which is just that final digit. And putting one together is super easy. Say you have the number 34. The stem is 3, the leaf is 4. Simple, right? You just group all the leaves that share the same stem and then line them up in order. It's a really fast way to sort and visualize your data all at once. And here is the absolute most important thing to remember about this method. While other tools, like a histogram, will group your data and make you lose the original numbers, the stem and leaf plot is different. You can look at this plot and perfectly reconstruct all of your raw data. Absolutely zero information gets lost. You can even get fancy and use it for some powerful comparisons. This is a back-to-back plot. We've got Class A on the left and Class B on the right, and they're sharing that middle stem. Now, to read Class A, you have to read from the center outwards. So that's scores of 65, 68, 69. For Class B, you just read it normally, 62, 64, 67. So what does this actually give us? Well, it means with a single glance, you can immediately start comparing the two groups. Does one class have higher scores? Is the data in one class more spread out than the other? The whole story of both data sets is laid out right there, side by side. It's pretty cool. But what happens when you have hundreds or even thousands of data points? Trying to plot every single one would get messy and frankly impossible. That's when we need to pull out a different tool, the histogram. It groups data together to show us the overall pattern, which means we sacrifice those individual details to get some big picture clarity. Now, before we can even build a histogram, we have to know what kind of data we're dealing with. Is it discrete or continuous? Discrete data can only take on specific countable values, like, say, the number of kids in a family. You can have 2 or 3, but not 2.5. Continuous data can be anything within a range, like a person's height. This difference is absolutely critical for how we build our chart. Okay, for discrete data, it's pretty straightforward. Each unique value gets its own bar, and you center it right over that number. The height of the bar tells you the frequency, how many times that value showed up, and really importantly, the bars touch each other. So why do the bars touch? It's not just a style choice, it's a really important detail that tells you you're dealing with numerical data on a continuum. See, unlike a regular bar chart for separate categories like red or blue, the numbers 2 and 3 are directly connected on a number line, right? The touching bars show that mathematical connection. For continuous data, we have to make our own groups, or classes. The class width is what decides how wide each bar is going to be. You figure this out by taking the range of your data, deciding on how many bars or classes you want, and then you divide. But here's the one rule you cannot forget. You always round that result up. Always. Why? It's to make absolutely sure your highest value has a place to go. And this right here, this might be the most important rule of all when you're setting up those classes. They cannot overlap, ever. If one class ends at 19, the next one has to start at 20. Think about it. If they overlapped, where would you put the number 20? Every single data point needs one and only one place to call home. No exceptions. So, we've built our plot. Now what? Well, now comes the really fun part, interpreting the story it's telling us. And we do that by looking at its overall shape. I bet you've seen this one before. It's the classic bell-shaped or symmetric distribution. You know, most of the data is piled up right in the middle, and then it slopes down pretty evenly on both sides. Things like IQ scores or people's heights in a big population often follow this nice, clean pattern. But what happens when the data isn't so perfectly symmetrical? Well, if you have a chart where most of the values are bunched up on the left side, but there's this long tail stretching way out to the right, we call that skewed right. The perfect example is income. Most people earn a relatively modest amount, but a few outliers earn a huge amount, and they pull that tail out to the right. And the exact opposite of that is skewed left. In this case, most of the data is clustered on the high end, over on the right, with a long tail stretching out to the left. A good way to think about this is retirement age. Most people retire in their 60s or 70s, right? But a few people manage to retire super young, creating that long tail on the left side. Now, if you ever get confused trying to remember which is which, just keep this one simple rule in your head. The tail tells the tale. Whichever direction that long tail is pointing, that's the direction of the skew. It's really as simple as that. All right, so we have now seen 3 awesome, powerful tools for visualizing our data. The big question is, how do you know which one to use and when? Let's do a quick recap to make that choice nice and easy for you. Here's the cheat sheet. If you've got a small, simple data set, a dot plot is probably perfect. If you've got a small to medium set where you absolutely cannot lose any of the original data points, then the stem and leaf plot is your best friend, for sure. And finally, for those really large data sets where the overall shape is what you care about more than individual values, the histogram is the way to go. So, I'll leave you with this to chew on. We know that in most places, home prices are skewed right. So what does that shape actually tell you about the difference between the average home price you hear on the news, which gets pulled way up by those huge mansions in the tail, and the price of a truly typical home, where most people actually live? See? That's the power of seeing the shape of the story, not just falling for a single simple number.